Acids and bases for IGCSE Chemistry. The board is Cambridge and the syllabus code is 0620. This is syllabus unit 7. So what does the unit and the syllabus actually look like? So it's comprised of 7.1, which focuses on the characteristic properties of acids and bases, 7.2 for oxides, and 7.3, which is for the preparation of salts. The pH scale. So the pH scale is a scale from 0 to 14, 7 being neutral. So from 0 to 6, it shows acidic properties, and from 8 to 14, it shows basic properties. The lower the pH, the more acidic the solution is, and this is because there is a higher concentration of H+ ions. However, the higher the pH, the more basic a solution is, and this is because there is a higher concentration of OH- ions in solution. Moving on. So here are some examples of the pH scale and some substances. For example, blood, which has a pH of 8, bleach, which has a pH of 13, and gastric acid, which has a pH of 1 or 2. So what do we exactly use to measure pH? The most prominent ways that we use to measure pH is by using something called universal indicator. So this is an indicator that shows you a pH of a specific chemical using a color code system. So this is basically what a universal indicator is. You can see that there are specific colors for each pH. In experiments, we also use something called a pH electrode, and this contains basically a pH meter. So the pH electrode basically contains sensors that measure the pH of a substance. This often comes in automated systems and different experiments. Here are two other indicators that we also use. The first one is litmus, and the second one is methyl orange. So, the litmus, there's two types of litmus here. There's blue litmus and red litmus. The difference between the two are that blue litmus turns red in acidic conditions, while red litmus turns blue in basic conditions. There are two different types. And if you are wondering what happens to blue litmus when it's in basic conditions, it stays blue. Otherwise, here we have the methyl orange indicator, and normally in neutral pH, it's yellow or orange, and in acidic conditions, it becomes red. In alkaline conditions, it becomes yellow or orange. Here are the different lists of different indicators that we need to know for our syllabus. It's comprised of the litmus solution, which is basically the same thing as litmus paper, but it's combined, so it turns red in acidic and blue in alkaline conditions. Next, we've got litmus paper, which we've looked at already. We've also looked at methyl orange. And next, we've got phenolphthalein and thymolphthalein. In alkaline conditions, phenolphthalein turns pink, and in alkaline conditions, thymolphthalein turns blue. So they both stay colorless in neutral and acidic conditions. Now we're going to be looking at acids and bases. This is more into 7.1 of the syllabus. Acids. So there are three main acids that we need to know, one being hydrochloric acid, the next being sulfuric acid, and lastly we've got nitric acid with these corresponding symbol equations. There are two defining features of acids. One being that they form H+ ions when dissolved in water. We'll see what happens and the differences between when it doesn't and does form H+ ions. Next, we've got the fact that acids donate protons, otherwise known as H+ ions. These can be used unanimously because H+ ions are so small and tiny that they can be referred to as just protons. More about acids. So a compound is considered an acid because of its ability to dissociate to produce H+ ions when dissolved in water. So we saw that this is a defining feature of acids. So for example, if we have both hydrogen chloride and hydrochloric acid, how do we know the difference? So by looking at this diagram, it's much more clear. So hydrogen chloride, we see there's a bond between hydrogen and chloride. However, in hydrochloric acid, we see that the H+ ions are dissociated, so they're alone, so they're not bonded with chlorine ions. And this is what it gives its properties. Hence, hydrogen chloride is just no acid. It doesn't have any acidic properties, while hydrochloric acid does. And we can see the dissociation of hydrochloric acid here. Okay, acids. The concentration of H plus ions determine the strength of an acid, as we said earlier. So we have two different types of acids, basically strong acids and weak acids. The main part about acids are that strong acids completely dissociates or ionizes in aqueous solutions, while weak acids only partially ionizes in aqueous solutions. So strong acids have a higher concentration of H plus ions, and weak acids obviously have a lower concentration of H plus ions. Strong acids will have a lower pH, and weak acids will have a slightly higher pH, below the pH of 7. So strong acid will sit somewhere here, while a weak acid will sit somewhere here. Okay, so the examples that we need to know are hydrochloric acid and ethanoic acid. So hydrochloric acid dissociates completely to form H plus ions and chlorine ions, while ethanoic acid here dissociates partially, which is the reason we have a reversible, is because it only dissociates partially, so there are still molecules of acid present after the reaction. And we form H plus ions, and we also form acetate. Bases. So the main bases that we have to know and the facts that we have to know are that generally metal oxides and hydroxides are bases, and that carbonates are also bases. What are the different features of bases? Firstly, it reacts with an acid, and they form OH minus ions when they're dissolved in water. Bases are proton receivers, so it's starting to make more sense now. Bases receive protons while acids donate protons. A soluble base is called an alkali. That's the main difference between a base and an alkali, as you can see here. Moving on, bases. So just like acids, bases also have strong bases and weak bases. So the concentration of OH minus ions determine the strength of a base. So strong base here, we see that they completely ionize in aqueous solutions, so they release lots of OH ions. So a strong base has a high concentration of OH minus ions and there's a higher pH. And an example here, all hydroxides of alkali metals are strong bases. So alkali metals are stuff such as lithium, sodium, potassium, rubidium, cesium, francium, stuff like that. Here, we've got an example of sodium hydroxide dissociating completely to form sodium ions and hydroxide ions. Okay, and just like acids, we also have weak bases. So weak bases have a lower pH, right? Weak bases have lower electrical conductivity and they also have slower rate of reaction. And the main part of this is that weak bases partially ionize in water and they give off small amounts of hydroxide ions. And just like the acids, it's denoted by a reversible arrow. So we have an example here of ammonia. Remember that this is ammonia and this is ammonium because it's an ion. And it basically reacts with water to form hydroxide ions and ammonium. We're going to be looking at neutralization reactions. So by looking at neutralization reactions, we'll be able to make more sense on the facts we've gotten so far about acids and bases. So neutralization is basically the reaction between an acid and a base. So an acid and a base, we'll see later, it forms a salt and water. If we look at the properties we saw earlier, acids give out H plus ions when they're in water and when they're in solution, and bases give out OH minus ions. So if you imagine we react these two together, it's going to form a salt, obviously, and water. So the basic ionic equation here is H plus ion plus OH minus ions form water. So that's the reason why this is called a neutralization reaction, because it forms a neutral solution. Okay, so we have acids and bases. So if we remove these spectator ions, we're left with the ionic equation. What basically are spectator ions? Spectator ions are ions that aren't taking part of the chemical reaction, and they're also present in both sides of the reaction. Acid reactions. So acid plus metal forms a salt and hydrogen. So we have an example here of hydrochloric acid, magnesium, forming magnesium chloride and hydrogen. Next, we've got acid plus base forms a salt and water. Remember, a base is metal oxides or metal hydroxides. We have an example here with sulfuric acid and copper oxide. Next and lastly, we got acid plus carbonate forms salt, water, and carbon dioxide. Here we see that hydrochloric acid reacts with sodium carbonate to form sodium chloride, water, and carbon dioxide. Base reactions. This is the same reaction we saw earlier, basically with sulfuric acid and copper oxide reacting. And this is the important part of base reactions. A base will react with an ammonium salt. An ammonium salt is something like NH4Cl, right? To form a salt, ammonia, and water. So if a question asks how you displace ammonia from an ammonium salt, the answer is to react it with a base. Oxides. What are oxides? So there's 4 types of oxides. There are basic oxides. Basic oxides are metal oxides. Well, most. And an example of this is something like potassium oxide, sodium oxide, calcium oxide, magnesium oxide, copper oxide, all of that. And conversely, we see that non-metal oxides are acidic oxides. Examples are sulfur dioxide and nitrogen monoxide, nitrogen dioxide, and carbon dioxide. We know from the environment unit that sulfur dioxide and nitrogen dioxide dissolve in rainwater to form acid rain, right? This is really important. It forms acid rain. And the reason for that is because it's an acidic oxide. This acidic oxides will also turn litmus paper red, as we saw earlier, and it will also neutralize bases. It'll also undergo acidic oxide plus basic oxide reactions. Next, we've got neutral oxides and amphoteric oxides. The difference between the two are that neutral oxides do not react with bases or acids. So they can't react with both acids or alkalis. And examples of this are water, nitrogen dioxide, and yeah. Next, we've got amphoteric oxides, and conversely to the neutral oxides, they can react with both acids and alkalis. More on amphoteric oxides. So amphoteric oxides are oxides that react with either a base or acid to form a salt and water. So we know that they have both acidic and basic properties by looking at their equations. So the 2 main examples we have to know, by the way, are aluminium oxide and zinc oxide. If we look at the example of zinc oxide here, it reacts with both sodium hydroxide and nitric acid to form a salt and water. So they both are proton acceptors and proton donators. So these are really cool oxides. Moving on, salt preparation. So we saw that this is the last part of our syllabus. The basics of salt preparation. What is a saturated solution? A saturated solution is a solution in which no more solute can be dissolved at that given temperature. Here we see that this is a salt, that's a solvent, and that's a solution. A hydrated substance is a substance that is chemically combined or bonded with water, while an anhydrous substance is a substance that contains no water. What exactly is a salt? A salt is a compound formed when a metal or an ammonium group replaces hydrogen in an acid. So this will make more sense later. How do we name salts? So we do name of metal and this acid ending. For example, if we have calcium and hydrochloric acid, it will be calcium chloride, and etc. Lastly, what is water of crystallization? Water of crystallizations is basically the water molecules present in hydrated crystals, including copper sulfate bonded with water and cobalt chloride bonded with water. There should be 5, but we're going to skip over that. And the solubility rules that we need to know, basically. Firstly, that all nitrates are soluble. Then all chlorides or halides are soluble except for silver and lead. All sulfates are soluble except for calcium, barium, and lead. And all sodium, potassium, and ammonium salts are soluble. And all carbonates are insoluble except for all sodium, potassium, and ammonium salts. And all hydroxides are insoluble except for all sodium, potassium, and ammonium salts. Okay, so there are 3 ways of preparing soluble salts. The first way, we make it by using salts from metals and insoluble bases. So from here, we have salts from metals. This method is only used for metals above hydrogen in the reactivity series, as copper, silver, gold, all this is too unreactive. So we use all of this. However, we have to also make sure we don't use extremely reactive metals, such as the group 1 alkali metals, as they are too violent of a reaction. So we use a titration method for them. So basically, this method is suitable for metals in this boundary. Okay, so salts for metals. The first thing we're going to do is warm the acid. So the acid is a limiting reagent, and this is done for speed. Secondly, we're going to add an excess reactant and stir it. Thirdly, we're going to filter the mixture. And fourthly, we're going to transfer the filtrates into the evaporating basin, where we're going to heat using a Bunsen burner. And lastly, or almost lastly, we're going to leave to cool until the crystallization point. And then we're going to be washing the crystals with distilled water. Distilled water because it contains less impurities. Then we're going to dry crystals on filter paper. We're going to move on to the second part. So this is preparing soluble salts from insoluble bases. So this is used to make salts that are low in the reactivity series, for example, for something like copper oxide. And we see here there's a reaction going on with copper oxide plus sulfuric acid, and this forms copper sulfate plus water. And we can see that here. Lastly, for preparing salts that are soluble, we're going to be using the titration method. So it's used for making salts of group 1 metals, so basically alkali metals and ammonium salts. We do this because of the reactivity. Okay, so basically in this acid-alkali titration, we're measuring how much acid is going to be needed to react with an alkali solution, so how much acid is needed to reach an endpoint. So here we have to use an indicator, but we don't know which indicator until we look at what acid and alkali. For example, if we have strong acids and strong alkali, we're going to use any indicator. However, if we have a weak alkali and a strong acid, we're going to use methyl orange. And lastly, if we have weak acid and strong base, we're going to use phenolphthalein. Okay, so the steps are, firstly, you're going to place a known volume of alkali into a conical flask using a volumetric pipette. Secondly, you're going to add an indicator, depending on what indicator we got from what acid and alkali we use. Then we're going to do the actual titration, where we add the acid using a burette. First, you have to measure it, and you have to get the endpoints with how much is needed to neutralize the acid. Then we're going to record the volume of acid added by measuring the titer. Then we're going to repeat it without an indicator. Then we're going to transfer it into an evaporating basin, heat it, leave to cool until crystallization point, and then wash it with distilled water and dry crystals. You see that this is basically a repeat. Lastly, we've got making insoluble salts. So basically a precipitate is an insoluble solid made from one or more soluble reactants. So 2 soluble reactants will create an insoluble insoluble substance, which is known as a precipitate. So we do this by first identifying the ions present in a soluble salt. For example, if I chose to do lead chloride, then we'll know that there is Pb2 plus and Cl minus, and use out the solubility rules to choose soluble compounds using these ions. So lead nitrate and sodium chloride are both soluble, so they're going to react together, right? And basically it's going to form lead chloride. It's going to form an ionic lattice of lead chloride, and the sodium and nitrate ions will remain in solution. This is a good diagram. Then we're going to filter off the precipitate and wash it and dry off the solid. So that is it, everybody. Thank you. Thank you so much.